Hello everyone, welcome to our nearly carbon neutral geometric topology conference. My name is Donghao. I'm a fifth year graduate student at MIT working with Professor Tom Rovka. This talk is under the session Reason Techniques in Floer and Khovanov homology. The title of this talk is Monopole Floer homology for three manifolds with toroidal boundary. This is going to generalize the work of Graham and Rovka for closed three manifolds. This talk will be divided into two parts. In the first part, I will first review the classical theory of monopole Floer homology for closed-oriented three manifolds. After that, I will discuss the generalization for three manifolds with toroidal boundary. I will sketch the construction and summarize some of the formal properties that are available so far. The title of this talk is slightly inappropriate because this invariant is really defined for a pair. Is defined for such a three manifold together with a suitable closed two form. In the beginning, we wanted to produce some invariant for a single three manifold, but later on we realized that it is necessary to incorporate such a two form in order to make the whole construction work. This is very unfortunate, but I hope this is also forgivable because we can still generalize the classical result in an interesting way and make some partial progress towards about the monopole theory. So I hope you will find this part interesting. In the second part of this talk, I will switch to the analytic side and explain the relation of this construction with Landau-Ginzburg models. For people who are interested in this story, you can find this part in the second video associated to this talk. So let's get started, and let me first explain the classical theory for closed three manifolds. So let Y be a closed-oriented three manifold, and we'll choose the closed two form omega as a sort of perturbation of the Floer theory. Then in these books of Graham and Rovka, they define three flavors of monopole Floer homology groups for such a pair, and they fit into a long exact sequence like this. In their book, they also prove that if the cohomology class of omega is non-zero, then the third group here, this bar version group, is always trivial. So the first two groups are isomorphic. In this case, only one flavor exists. In this talk, let's denote this from version group by HM star. This group is defined over a Novikov field, and it is always finitely generated. This homology group is bigraded. It naturally carries homology grading and additional grading by spin C structures. So you can always write it as a direct sum like this. I'm not going to tell you what are spin C structures in this talk, but let me just say spin C structures on this three manifold are classified by their first chain classes if H upper 2 of Y has no two torsions. So in this case, this map sending a spin C structure to its first chain class is always injective. This monopole Floer homology has two important properties that we'll generalize later for three manifolds with toroidal boundary. So let me first give you a brief summary. The first property is a TQFT structure, meaning whenever you have a four manifold cobordism W from Y1 to Y2, we can construct a cobordism map between their four homology groups. Moreover, this assignment is functorial with respect to compositions of cobordisms. In this way, we obtain a functor from a cobordism category to the category of groups. The second property is a computation for the graded Euler characteristic. So here, for each spin C structure S, we can take the Euler characteristic of the summand. In this way, we obtain a function on the space of spin C structures. Then this theorem says if the first Beatty number of Y is at least 2 and the cohomology class of omega is non-zero, then this function will recover the Müller-Churoff torsion invariant of Y up to an overall sign ambiguity. This result was first due to Montops in 1996 and refined by Churoff 2 years later. The upshot here is that the distortion invariant is a classical algebraic invariant of Y. It can be computed in terms of some cellular chain complex of Y with a suitable local coefficient system. So we have a pretty good understanding of this graded Euler characteristic function. We'll come back to this Montop's paper later and generalize these two properties for three manifolds with toroidal boundary. But for now, let me sketch the construction of this group first. So how are these invariants defined? This four homology group is defined as an infinite dimensional Morse homology. Given any spin C3 manifold decorated by a closed two-form omega, we will first generate an infinite dimensional space C of y called the configuration space, which is acted on by infinite dimensional gauge group G of y. Over this configuration space, there is a naturally defined Chern-Simons Dirac functional, which is invariant under this group action. This also means that this functional will never be Morse on this configuration space. So the right thing to do is to consider this quotient space and look at the consider the Morse homology of this functional on this quotient configuration space. The two-form omega here is used to perturb this functional. In the end, we'll make it Morse on this quotient configuration space. A critical point of this functional is also a solution to the monopole equations or the Seiberg-Witten equations on this closed three manifold. I'm not going to explain the various terms in this expression, but for experts, I'm perturbing the curvature equation using this closed two form. And when the cohomology class of omega is generic enough, this will rule out reducible solutions. So this is the first step. We'll take all the critical points of this special functional and generate a vector space. The second step is to define the differential map on this chain group. To do so, we have to consider the four-dimensional monopole equations on this product four manifold R cross Y. And our four homology is just the homology of the resulting chain complex. In order to define the cobordism map in the previous slide induced by such a four-manifold cobordism, we have to consider the following completion of W. So here we'll attach a cylindrical can to this incoming boundary Y1 and attach another cylindrical can to this outgoing boundary Y2 to obtain a complete Riemannian four-manifold. Then the cobordism map is defined by counting the zero-dimensional solutions on this complete Riemannian four-manifold. So the construction is analytic. To further motivate our work for three manifolds with toroidal boundary, let me tell you a little bit about not-Floer homology. There is a parallel development of Floer theory that uses Heegaard splittings of closed three manifolds called Heegaard-Floer homology. This was introduced by Professor Oswald and Szabó around 2000 as the symplectic replacement of gauge theory. We now know that these two theories are more or less equivalent for closed-oriented three manifolds, but there is one extra flexibility in their theory. Their invariants can be also defined for a pair for not inside a closed three manifold. The two simplest versions are the hat version and the minus version, and they were introduced by Oswald and Szabó and independently Rasmussen around 2003. And it is very natural to ask what's the similar construction in the Seiberg-Witten world. The first attempt in this direction was made by Kramer and Moravka in 2010, based upon the suture manifold theory developed earlier by Jonas. This interaction between suture manifold theory and Floer theory is quite remarkable, but I think the only problem is if you really follow this approach, then the TQFT structure is relatively difficult to verify. So this was only proved by Jonas in 2016 that this suture Heegaard-Floer homology is a functor from the suture cobordism category. And the similar result was only obtained by Zheng Kun 3 years ago in the Seiberg-Witten theory. I think part of the problem here is that this monopole not-Floer homology is defined in a rather indirect way. So let me give you a few more detail here. So let's consider a knot inside this three sphere and take this link complement. Here, M is a meridian of this knot. So this complement has two boundary components. Now we use a suitable orientation reversing diffeomorphism phi to identify these two components to obtain a closed three manifold denoted by S3 of K, comma phi. Then the not Floer homology of K is defined as the monopole Floer homology of this closed three manifold. And the ambiguity arises from this diffeomorphism. And there are many different choices, and somehow we have to verify for different choices of phi, these groups are isomorphic in a canonical way, and constructing cobordism maps is even more challenging. At this point, one may ask, can we have a more direct definition of this monopole Floer homology? For instance, can we construct the Floer homology of this link complement directly by studying the monopole equations on this space? And maybe in this way, we can construct the cobordism map analytically. We are going to address this problem in this talk, and the idea goes back to the Monopole paper. There are two essential ingredients. First, we have to specify which metric we want to work with on this space. Secondly, we have to specify the two-form perturbation. So let me tell you the setup in more detail. In this picture here, Y is a three manifold with toroidal boundary. Its boundary sigma is a union of two tori. It can be disconnected, and each boundary component is a two torus. The genus is one. And then we will choose a flat metric for the boundary and choose an arbitrary extension of the Riemannian metric to the interior of Y. After that, we attach cylindrical cans to this compact piece Y to obtain a complete Riemannian manifold. Let's denote this completion by Y hat, and this is a picture for this completed manifold. So this is the metric we are going to work with, and this space Y hat is non-compact. The second step is to specify the two-form omega, and in our case, we want this two-form omega to have the standard shape mu plus ds wedge lambda over this cylindrical can. Here, S is the spatial coordinate for this cylindrical can. Mu is a harmonic two form on the surface, and lambda is a harmonic one form. At this point, we have some technical conditions for this two form. First, over each boundary component, both lambda and mu are non-zero. Secondly, this class of hard star of lambda lies in the image of H upper 1 of Y. Some of the conditions here are not really necessary for defining the group, but all of them are very important for the properties I'm going to state momentarily. I don't really have time to explain why this is the case. The first condition here will force the boundary of Y to be disconnected because omega is closed on the three manifold, so its integral over the boundary is necessarily zero. But for the purpose of this talk, let's focus on this special case for the sake of simplicity. As I mentioned earlier, this setup is borrowed from this seminal paper of Monopole's. We have already seen their results before, which says for any closed-oriented three manifold with B1 at least 2, this gradient Euler characteristic function will recover this torsion invariant of Y. The fact is, in the same papers, they prove the same result for any three manifolds with toroidal boundary. So their results are actually much more general. This is what happened in this Monopole paper. Back to 25 years ago, we didn't yet have a Floer homology group, but defining this gradient Euler characteristic is a much easier task. It's enough to take the sign count of critical points of the Chern-Simons Dirac functional. So in this Monopole paper, they worked with this three manifold with cylindrical cans, and they worked with this two-form perturbation, and they defined this function by counting critical points of that special functional, and verify that this function will recover this torsion invariant even for a three manifold with toroidal boundary. So they only took the first step in their paper, But maybe we can go one step further and analyze the negative gradient flow line of the Chern-Simons Dirac functional and define a Floer homology group. This will force us to consider the monopole equations over this product for manifold R cross Y hat. But because our three manifold Y hat is already non-compact, this product manifold is somehow non-compact in two directions, in the time direction T and in the spatial direction S. And this Floer manifold carries a planar end that looks like the upper half plane cross sigma. Here I'm using the Euclidean metric on the upper half plane. And over the planar end, the monopole equations are perturbed by the standard two form omega. So the geometry of the Floer manifold is very different, and we have to understand the monopole equations very concretely over this planar end. This is going to be the task for the second part. So before we switch to the analytic side, let me first assure you that this construction will indeed work. This leads to the main result of this talk. This is the main theorem of this talk, which says under above assumptions of this closed two form, for any three manifold with disconnected toroidal boundary, this monopole Floer homology is always well defined. It carries a natural homology grading and additional grading by relative spin C structures. A relative spin C structure is a spin C structure on Y with a fixed trialization near the boundary. So their first chain classes now lie in the second relative cohomology group of Y. And our next step is to understand the invariance of this group. And the best we can say at this point is the following. First, this group is independent of the interior metric Y and the flat metric of the boundary. Secondly, this group depends at most on the cohomology class of omega and the cohomology class of Hart star of lambda. Finally, this group is finally generated over a Novikov field. So in this case, we do have some very nice topological invariant. When the boundary of Y is connected, if we choose this flat metric of the boundary carefully, then one can still define this for a homology group. Some of the properties here are not true anymore. The next thing I want to say is the TQFT structure, as I advertised earlier. So in this picture, each Yi is a three manifold with toroidal boundary, and the cobordism between them is necessarily a full manifold with corners. So here, this horizontal manifold W is a cobordism from the boundary of Y1 to the boundary of Y2. Such a cobordism is called strict if this horizontal manifold W is a standard product. This is a pretty restrictive condition. It forces the boundary of Y1 to be identical to that of Y2. But in this special case, one can indeed construct the cobordism map between their four homology groups. The construction is again analytic, and let me give you a brief sketch here. So the first thing we do is to attach a cylindrical end in the spatial direction to this four manifold with corners. In this way, we obtain a cobordism from the completion of Y1 to the completion of Y2. After that, we will attach cylindrical ends in the time direction to obtain a complete Riemannian four manifold, which also carries a planar end that looks like the upper half plane cross sigma. Then this cobordism map is defined by counting the zero-dimensional solutions of the monopole equations on this space. So again, the construction is analytic. This theorem is pretty good, but still we are not very happy because we really want to remove this assumption on this horizontal manifold. We do have such a generalization in that case, but the statement will become slightly different. So in general, if we don't make any assumptions on this horizontal manifold, then we will obtain a map from this tensor product to the Floer homology of this outgoing boundary. In some sense, the Floer homology group of this horizontal manifold W is parametrizing all possible maps if one can obtain from this four manifold with corners. In order to recover the cobordism map in the previous slide, note that for the standard product perturbed by the standard 2 form, its monopole Floer homology is isomorphic to the base field canonically. So if you plug in the canonical generator in the second entry here, then you can recover the previous cobordism map. So this is the generalized TQFT structure. The last structural result I want to state is a gluing theorem. So in this picture here, each black dot represents a union of two tori, sigma I, decorated by some harmonic 1 forms lambda I and some harmonic 2 forms mu I. And each horizontal segment represents a 3-manifold cobordism between them. Whenever we have 2 such cobordisms, we can take the composition to obtain a cobordism from sigma 1 to sigma 3. Then this term says one can always construct a gluing map from the tensor product of 4 homology groups of these gluing factors and end up with the 4 homology groups of this composition. Moreover, if we assume each mu I is non-vanishing on the surface sigma I, this gluing map is always an isomorphism. Here's a word of warning. This theorem is subject to certain limitations because when 2 such 3 manifolds are glued along their common boundary, their 2 forms are required to agree with each other over this overlapping region. So this imposes a non-trivial condition on the way they are glued. This theorem is not very mysterious. Its proof uses Floer's excision theorem. This gluing map alpha is induced by a concrete 4-manifold straight cobordism from the completion of W12 union the completion of W23 to the completion of the composition and the standard cylinder across sigma 2. Here is a picture of this cobordism, and I'm drawing this straight cobordism vertically. So this red rectangle represents a time interval I cross W12, and this blue rectangle represents a time interval cross W23. In the middle, we have a saddle cobordism cross sigma 2. On the top of this cobordism, we have the completion of W12 and the completion of W23. And on the bottom, in the front, we have the composition W13. And on the back, we have this standard cylinder R cross sigma 2. So the proof uses some existing technique and it's not very mysterious. Nevertheless, I still find this theorem particularly useful, and you can easily derive many useful corollaries. The first application here will allow us to recover the not-Floer homology. To apply this theorem, let's take sigma 1 and sigma 3 to be empty sides, and sigma 2 to be the union of 2 tori. The first gluing piece W12 is going to be this link complement. And the second gluing piece is the standard product. And then this gluing theorem says the monopole Floer homology of this link complement is isomorphic to the monopole not-Floer homology of K. This is because the Floer homology group of the second piece is pretty standard. It has rank 1. So this is the first application. The second application here is about connect sum formula. Here, each yi is a 3-manifold with toroidal boundary, and you can imagine the connect sum is happening near some of the boundary components. So you can obtain this connect sum from this gluing process. On the left-hand side, we have this disjoint union of y1 and y2. On the right-hand side, we have the connect sum of this standard cylinders. Then the gluing theorem will allow us to write the Floer homology group of this connect sum as the tensor product of 3 factors. The Floer group of this last piece can be computed very concretely. It has rank 2 and they concentrate in 2 adjacent homology gradings. One can also consider the connect sum with a closed oriented three-manifold. Again, imagine the connect sum is happening near one of the boundary component. Then here we will have the connect sum of the standard cylinder with this closed three-manifold M. The Floer group of this guy can be identified with the tilde version of monopole Floer homology of M. And these two connect sum form are also comparable with the ones for suture Kigar for homology. This is the end of the first part. To summarize, our monopole Floer homology categorizes the mu neutral of torsion invariant, satisfies a pretty reasonable TQFT property, and there is a simple gluing result. However, in order to make the whole construction work, there are many difficulties to work out. In the second part of the talk, we will focus on one particular problem and explain why non-logismal models are useful for the proof. For people who are interested in this story, you can find this part in the second video associated with this talk. Part 2 is almost independent of the first part, and we'll start with the basic definition. This is the end of the first video. Thank you so much for your attention. Goodbye.